why did I use salt bridge here? The salt bridge maintains electrical neutrality. Okay, it maintains the neutrality of the solution. How? If you see here, when the zinc is losing electrons, okay, the Zn2 plus ions are released into the solution. Okay, so this complete solution will become a positive solution. Okay, at the same time, here the Cu2 plus ions taken the electrons from the copper rod. Okay, this Cu2 plus is completely became Cu and it is deposited here as a Cu solid. Okay, but SO4 minus 2 ions are left here. Okay, now the complete solution is negative. The complete solution is negative solution. Before oxidation, it is a neutral solution. Now it is a completely positive solution. Before reduction, this is neutral solution. Now it is completely a negative solution. So what does salt bridge contains? Salt bridge contains another electrolyte. Okay, like K2SO4. This K2SO4, it has two ions like okay, I am taking here SO4 minus 2 ions. At the same time, it contains K plus ions. So this SO4 minus 2 ions, it is a positive solution. So it comes here, okay, through the salt bridge. This negative charge and this positive charge are completely neutralized. At the same time, this is completely a negative charge. So this positive charge comes from the salt bridge and it is connected with the negative charge. It can be completely neutralized. Okay, now the solution is neutralized. Again, okay, the current flow is starting. So this is how the salt bridge is working. Okay, so the salt bridge maintains electrical neutrality of the solution. Salt bridge maintains electrical neutrality. Neutrality of the solution. Okay, salt bridge maintains neutrality of the solution. At the same time, the salt bridge avoids liquid-liquid junction potential. So, salt bridge avoids liquid-liquid junction potential. Liquid junction potential. So, okay, instead of two vessels, I am taking here only one vessel. Okay, this vessel is divided into two parts. Okay, this is a semi-permeable membrane. Semi-permeable membrane. Okay, I am taking here. So instead of two containers, I am taking here one container. So I am here taking zinc sulfate solution. Okay, I am keeping here one electrode. This is zinc electrode. It is acting as anode. Okay. At the same time, I am taking here the copper electrode. Okay, here electrolyte is copper sulfate solution. This is copper electrode. Here, this is cathode. We call cathode. Okay. Over here, I am connected to the external circuit, that is called voltmeter. So I am taking here internal circuit. Here it is salt bridge. Okay, the salt bridge here. Okay. The salt bridge maintains electrical neutrality. How it is electrical neutrality? For example, you observe here. In zinc sulfate solution, at anode always oxidation takes place. So zinc is losing electrons. So yes or no? Zinc is losing electrons. It forms Zn2 plus 2 electrons. So these electrons are accumulated on the rod. These ions are released into the solution. Now the complete solution will become positive. So here many Zn2 plus ions are there. The solution completely became positive. At the same time, copper is the at the cathode reaction takes place. This Cu2 plus gains electrons. It forms Cu. Okay, this Cu is deposited here. Okay. Now here SO4 minus 2 ions left here. Okay, SO4 minus 2 ions left. So the solution completely became a negative. It is positive solution. It is a negative solution. Okay. At the junction, what will happen? This negative charge ions, this positive charge ions, and this negative charge ions come close together because there is an attraction force between them. So here the positive charge ion, here this positive charge ion, here all the positive charge ion comes here. Then all the negative charge ions come here. There is an attraction force between the negative charge and positive charge ions. Okay. At the junction, there is a potential difference is generated. Okay, at junction there is a potential difference is generated. So that potential difference we call liquid junction potential. That we call liquid junction potential. That we call liquid junction potential. That is called liquid junction potential. Okay. So here there is no movement of electrons at the junction. If there is no movement of electrons, means there is no electricity. So to avoid this liquid junction potential, we have to use salt bridge. So the salt bridge maintains avoids liquid junction potential. So salt bridge avoids liquid junction potential. The salt bridge avoids liquid junction potential. How the salt bridge avoids liquid junction potential? Now we are going to discuss. In galvanic cell, we have used 2 electrodes. At the same time, we have used 2 vessels. Instead of 2 vessels, I am taking only 1 vessel. Okay. Instead of 2 vessels, I am taking only 1 vessel. So, for example, how to represent the chemical reactions in galvanic cell? The representation of galvanic cell. Okay, in galvanic cell, there is 2 electrodes are there. The first one is anode, and second one is cathode. Okay, at anode always oxidation takes place. Okay, at the cathode always reduction takes place. Okay, in between anode and cathode there is a salt bridge is present. What is one? Salt bridge. This is salt bridge. Okay. So here the direction of flow of electrons from anode to cathode. The direction of flow of electrons from anode to cathode. Next, the direction of flow of current, that is called the direction of flow of a current from cathode to anode. So this is the representation of galvanic cell. Now I am writing some chemical reactions you will understand easily. The first equation already we discussed it. Okay, at anode oxidation takes place. For example, take zinc. So zinc is Okay, it forms Zn2 plus aqueous. Okay, this is anode. This is salt bridge. So reduction, the copper. Now the copper is Cu2 plus aqueous. Okay, it became solid Cu. Solid Cu. So this is reduction. So this is one representation of the reaction. At the same time, in a chemical reaction, I will take here this is some AgMO3. AgMO3. Okay, if I take here one vessel, here I have taken here this is CuSO4. CuSO4. So these are connected here. Okay. Okay, electrodes. So if you want the reaction is taking place here. The reaction is right here. This is here oxidation. Like right here oxidation. That is Ag is solid. It undergoes oxidation. Okay, it forms Ag plus aqueous at oxidation. It is salt bridge. This is salt bridge. At reduction, okay, it forms Cu2 plus aqueous and forms Cu solid. Okay, this is how the chemical reactions are represented. One more equation right here. So you take, for example, here iron, it's a solid. It undergoes oxidation, it forms iron aqueous 3 plus. Okay, here is a salt bridge. Now the reduction, you can write here, this is cadmium. Okay, there is a plus 2. Cadmium Cd plus 2. Okay, it forms here Cd. It is a aqueous and this is a solid. So like that, the chemical reactions in a galvanic cell. So this is the way of representation. Thank you. Thank you.